Hey, what's up everyone and welcome to today's video. I want to show you a cool physics demo today that you can build using JavaScript. Now this demo was inspired by the 3 blue 1 brown video in which he showed that you can calculate the digits of pi using 2 colliding blocks. It's a really cool video and I definitely recommend checking it out. I'm going to put a link to this in the description. Anyway, I decided to build a physics engine to demonstrate this phenomenon. I'm going to show you that right now. So this is the demo that I built. And if you watch the 3 blue 1 brown video, you know that for certain mass ratios, the number of collisions starts to resemble pi. So for example, if I set the mass of block 1 to 1 and the mass of block 2 to 1 trillion and let this thing run, we're going to see that the number of collisions is going to look like 314,159,2. So yeah, it looks like pi. It's really crazy how that works. Watch the video by 3 blue 1 brown if you want to see the math behind it, but we're just going to jump into the code now. All right, we're in VS Code now. We're going to make 3 files really quick. We're going to have an index.html. We're going to have a style.css, and we're going to have an app.js. There's not much HTML in this project. I'm just going to run through it really quick. I'm going to generate some boilerplate with Emmet. I'm going to bump my font size up so you guys can see better. We're going to link up our CSS and our JavaScript real quick. Then we're going to add a canvas with the ID of canvas. Below that, we're going to have a div for all of our inputs. It's going to be our mass inputs and the play and reset button. I'm going to call that section controls. I'm going to create 2 divs with the class of group now. Inside these groups, we're going to get a label. And we're going to get a text input. All right, now we're going to make 2 buttons, one for starting and one for resetting. I'm going to fire this up on live server now so we can view it in the browser. And there we go, we got our unstyled app. Back into VS Code now, we're going to open up our style.css. I'm going to set the margin and padding to 0 and box sizing to border box. I'm going to pick a font for our app now and then set the background to a gray. I'm going to give our canvas a background of a lighter gray. I'm going to add some padding to our controls group. I'm going to add some margin on the bottom of our 2 groups within that control group. I'm also going to set the font size of all the inputs to 16 pixels. This is important for mobile browsers. If a font size inside of an input is less than 16 pixels, when that input gets focused, the browser is going to automatically zoom in, and that's kind of an annoying thing. So I just always set my inputs to at least 16 pixels. And last, I'm going to put some basic styles onto the buttons that we have. All right, that's our styles done. We're going to go back and take a look. It's starting to look a little bit better. And we're going to jump into the JavaScript now. First thing we're going to do is grab all the elements that we need. The next thing we're going to do is we're going to grab the context from the canvas. When you're dealing with the canvas, you're going to be working with something called the context. And we grab the context by saying canvas.getContext and then selecting 2D. Now, there are other contexts that you can grab. The canvas can do some really cool things with 3D effects. You can use things like WebGL and libraries like 3JS to do some really cool stuff. But for today, we're just going to be working in the 2D context. Next thing we're going to do is build an initialization function that's going to run when the document's ready. Inside here, we're going to set the canvas width and height. We want the canvas to be the full width of the window, and we want the height to be the full height minus 200 pixels. We're also going to initially set the reset button to display none and the play button to display block. And once that function's set up, we're going to call it when all the DOM content is loaded. I'm also just going to throw in a console log here so we know it's running. Moving back into the browser, I'm going to open up the DevTools. There we can see that init is in fact running. One other thing, when I resize the window, the canvas doesn't update, so we're going to fix that really quick. We're going to make a function called resize. And when this fires, we're just going to reset the canvas width and height. And this is going to be called whenever the window resizes. So we're going to put an event listener on that. All right, we're going to check to see if that worked. Yeah, and now it looks like it's working now. Okay, the next thing we're going to do is we're going to write a block class. So this is the class that we're going to use to create both the large and the small box on the screen. And it's going to take in 4 properties. It's going to take a mass, a position, a velocity, and a color. Inside this constructor function right here, we're just going to set those properties. The last property that's going to be on this box is size. And I want the size to be dictated by the mass. But since the mass of these blocks are going to range by a lot, like it could be 10 all the way up to a few trillion, what I'm going to do is just make it proportional to the amount of digits in the mass rather than directly proportional to the mass. So I'm going to say this size is equal to mass, convert that to a string, take the length of that string, and multiply it by 10. Now the first method we're going to define on this class is going to be the render function. This render function is what's going to be interacting with the context that we created above. So there's a method on that context called fillRect. This method will create a rectangle based off of 4 numbers: an x position, a y position, a width, and a height. Now, one thing you should know about how the canvas works is that the origin is going to be this upper left-hand corner. So this point up here is going to be 0x, 0y, and the more positive your y value gets, the further down you go. So this is kind of upside down compared to a lot of other coordinate systems where 0, 0 is going to be kind of the bottom left and positive y is going to be facing upwards. So that's just something to know. So our rectangle, we're going to want to draw that at the bottom of the canvas right here. So the first value is going to be our x, and we're going to set that to this position. The y we're going to set to the canvas height, which is the full height of the canvas, so it'd be at the very bottom, but then we're going to subtract the size of the box so that we're not off the screen. So we're going to subtract, and then both the width and the height are going to be this size. And one last thing real quick, right before we call this fill rectangle method, we're going to set the fill style to the color of that rectangle. And we're going to do that by calling context.fillStyle equals this color. All right, so that should do it for the block class right now. We're going to test this out by creating a new instance of that class. So in here, we're going to pass in 100, 40 pixels from the left, no motion, and this is going to be blue. Now what we're going to do is call render on this block, and we're going to do that up in the init function. And there we go. We got our first block down at the bottom there. So the next thing we're going to want to be able to do is update the position of this block. So we're going to add that method to the block class. Now inside of this function, we're going to say this position is equal to this position plus this velocity multiplied by some amount of time. And this dt here is going to be taken in as an argument. So what this is saying is if the box is moving at 5 pixels per second and 1 second goes by, we're going to add 5 pixels to the position of the box. And this line right here can actually be written a little bit more concisely. This is saying the same thing now. We're just adding this velocity times dt to this position. So in order to use this new update method, we're going to need to call it inside of a loop. And for this loop to actually keep looping, it's going to have to recursively call itself. We're going to do that through request animation frame. So if you're not familiar with request animation frame, it's similar to like a set timeout function where it's going to call whatever function you pass into it after a certain amount of time. But request animation frame is going to do it in a way that it'll sync up with your browser's frame rate. So on most browsers, this request animation frame is going to run at 60 frames per second. This request animation frame is also going to pass in a timestamp to the function that you're calling. So we're going to grab that as a parameter right here. We're going to call it timestamp. And then we're going to console log that right now to show it's working. And then we're going to call loop below that. So we're going to go back to the browser now. And you can see that this is just calling itself over and over again at 60 frames per second. In order to use that update method, we're going to need a DT, and we're going to calculate that by storing the value of the last timestamp and comparing it to the new timestamp. So right above this loop function, I'm going to declare a variable using the let keyword, which is going to let us reassign this variable, and I'm going to call this last time. And I'm just going to leave this undefined right now. Then inside the loop, we're going to say that dt is equal to timestamp minus last time, and we're going to console log that. Also, the first time this is running, we're not passing a timestamp into it, so we're going to fix that right now by calling it through request animation frame. Now we check the browser. We're getting not a number because we're not actually ever defining last time. So right after we calculate this dt, we're going to have to reset last time to be the current timestamp. And now we're only going to get not a number on the first time through. And the rest of these values are going to be 16 milliseconds, which is 60 frames per second. So now that we have a dt, we can actually use that inside of our update function. So we're going to call blk.update dt. And after we update it, we're going to render it again. And we're also going to give this a velocity of 10 pixels per second. And also, in order to not break this, we actually don't want to run this update the first time because we're going to get not number, and that's going to break things inside of our block. So we're going to fix that with an if statement. And we're also going to define last time beneath that if statement so that it doesn't run the first time. Give that a save. All right, so what's going on here is that I wanted the block to move at 10 pixels per second, but we're measuring time in milliseconds. So I'm going to go back and change one thing in our update method real quick. We're going to divide dt by 1,000, and that will convert that to seconds. All right, so now what we see is that the block's moving, but it also looks like it's stretching out. That's because we're never clearing those pixels. When you draw to the canvas, it doesn't reset what's already on there. So we're drawing the new block and we keep drawing it over and over again, but those last draws are staying there. So we're going to use a new method now called clearRect. We're going to call that right before we update and render our block. And we're just going to say context.clearRect. And again, this takes the same arguments as fillRect. So we're going to say we want to start at 0, 0, which is the top left, and then we want this rectangle to cover the entire canvas. We're going to say canvas.width and canvas.height. Give that a save. And we got a sliding block. So what we want to add now is some collision detection. The first thing we're going to be looking for is when the small block collides against the left side of the screen. So the first thing I'm going to do is flip the velocity on this block so that it actually goes to the left. So we're going to say negative 20. And the block just goes and flies right off the screen there. So what we're going to do is define a new function called checkWall. This function is going to receive a block as an argument. What we're going to do is we're going to look at the block's position and see if it's less than 0. And if it's less than 0, that means that the block has gone off the left side of the screen. So I'm going to call this function right after the update, and we'll see if that logs out collide. So back to the browser. There we go. Right when the block starts to leave the screen, we start seeing collide. So what do we actually want to do inside this if statement? The first thing I want to do is say that the block's position is equal to 0. This is just in case the block's moving so fast that it's already slipped off the screen. We're just going to pull that back into the frame. And then the second thing we're going to do is flip the velocity. So what this line is doing is saying that the block's velocity is equal to its current velocity times -1, and that's going to flip the direction. We're going to give that another save and check to see if that's working. There we go. We got one collide console logged, and the block's flipped around. So we're really starting to make some progress now. We know how to draw a block, update its position, show it moving along, and detect collisions with a wall. The next thing we're going to do is create the second block and figure out how to detect collisions between the two blocks and how to calculate their velocities after that collision. So first thing is to make two block instances now. We're going to call this block 1 and block 2. We're going to make block 2 red. We're also going to make block 1 a little bit smaller. And we're going to set its initial velocity to 0. And we're going to move block 2 further right. We also need to update what's happening inside our loop to deal with block 1 and block 2. Give that a save. We've got our 2 blocks right there. Getting BLK is not defined at line 15. And that's just us rendering that block on the first time. I'm going to get rid of this line right now. All right, no errors. We got our 2 blocks, and they're moving towards each other. To detect collisions between these 2 blocks, I'm going to make a second function and call it checkBlockCollision. I'm going to have this function taking 2 arguments for the 2 blocks. And what we're going to be doing now is setting up an if statement to check if block 1's position plus its size is greater or equal to block 2's position. So what this is saying here is that block 1, which is going to be the block on the left, plus the width of it, if that is overlapping with the start of the next block, we know that they're colliding. So right now we're just going to console log collide. I'm going to put this function up into our loop. So the second these blocks overlap, we should start seeing collide in the console. So there we go, that's working. So what we actually want to do inside of this if statement is change the velocity of the two blocks. Now these collisions are elastic, which means that there's no change to the total kinetic energy or momentum. The kinetic energy equation is Ke equals 1/2 mass times velocity squared. And the equation for momentum is just momentum is equal to mass times velocity. So because this is an elastic collision, we're saying that the kinetic energy of block 1 plus the kinetic energy of block 2 before the collision is the same after the collision. And we're saying the same thing about the momentum. It's the same before and after. So deriving the final equation we're going to use from these equations kind of takes a few steps. I'm not going to go through that right now, but if you guys want to see how that's done, there's a great video by Khan Academy explaining how to do this. I'm going to put the link to this video in the description. It does a pretty good job explaining everything, but we're just going to jump to the final product. And real quick, I'm going to define a couple new variables just to save some space in the equations below. So my first equation is going to be calculating the initial momentum. And this is just saying that momentum 1 is equal to m1 times v1 initial plus m2 times v2 initial. Our next equation is going to solve for v2 final. And once we have v2 final, we can solve for v1 final. Again, if you want to see where those equations came from, you can refer back to the video I mentioned. Now that we have the final velocities, we can update our block velocities. So this is just saying block 1 velocity is equal to v1 final, and block 2 velocity is equal to v2 final. We can head to the browser now and see if this is working. There we go. So we got our collisions going. So now that we're detecting all the collisions that we want to, we're going to add the collision count to the canvas. What we need to do first is add a count variable. I'm going to define that above the loop right here with the let keyword again. And every time there's a collision, we're just going to increase the count by 1. That's going to happen in 2 places. First in the check wall function, and also in the check block collision function. The last thing we need to do is display this count on the canvas. And we're going to do this with a new method on the context called fill text. Fill text takes in a string that we want to render out, and then an X and Y position. So I'm saying draw on the count and put it 10 pixels from the left and 20 pixels down. So we got a tiny little 0 up there. We're going to change the font and the fill of that actually right now. We're going to set the fill style to black. And we're going to set the font to 20 pixels Georgia. All right, so that's starting to look better. So right now, this loop starts running right away when the browser fires up. And that's not what we want. We want this to start when we click the start button. So we're going to implement that feature now. The first thing we're going to do is create a variable called quit. And if this variable is equal to true, we're not going to call request animation frame again. This variable is going to allow us to break the loop later on when we want to reset the canvas. We're also going to get rid of this initial call right here. And we're going to create a play function. Inside of this function, we're going to set quit to false and then call request animation frame on the loop. We're going to trigger this function when we click the play button. So we're going to add an event listener to that button now. So back to the browser, we have nothing initially, and then we click start and the canvas fires up. We're also going to hide the play button and show the reset button inside of this play function. So now when we click play, we get the reset button, and we're going to wire that functionality up right now. So a new function called reset. We're going to set quit back to true, and we're going to swap which button is visible again. So back to the browser, we hit start, and when we hit reset, it just pauses, and that's because that quit variable is breaking us out of the loop, but it's not really doing what we want. So we're going to add a few more lines of code into that reset function. So we want to reset the positions and velocities of both the blocks. So to make that easier, we're going to make some variables right now, which are going to hold those initial positions and velocities. I'm going to do that right up here before we create block 1 and block 2. And then inside of our reset function, we're going to assign block 1 and 2's velocities and positions back to these initial values. We're also going to reset the count and set that last time timestamp to null. Also, one thing we're going to do up in the looping function is we're not going to reset this timestamp unless we're looping through one more time. And that's because in that reset function, we're saying that last time should be undefined when this starts over again. But right after we call that, this function's just going to set last time to that timestamp again, unless this is happening inside of this quit block here. And since quit is going to be true, we're not going to redefine that last time, and we're not going to call that request animation frame again. So back to the browser now, we can click start, and when we hit reset, it just looks like it's pausing, but when we hit start again, it starts over from the beginning. So at this point, I actually want to break out all that render logic into its own reusable function. So up until now, all of this render logic is contained inside this loop here, but I really just want a function called render, and we're going to move all that down into that function. So what's nice about this setup now is that we can call render inside that initialization function, and we can also call it inside of the reset function. So now when we start the code, we're already going to see the blocks on the screen, and when we reset, we're going to see the blocks back in their initial position. So we're going to check that out now. So yeah, as you can see, the blocks are already on the screen, whereas before they weren't showing up until we clicked start. And now when we click start, it goes, and when we click reset, they pop back to their spots. So we're getting pretty close to done now, but we want to be able to update the mass of the two blocks. So we have these two mass inputs here, but they don't really do anything now. So we're going to make a new function called update mass and connect it to these inputs. So right here, we're going to do function update mass. And this function is going to take in two arguments. First, it's going to take a mass value, which is going to be whatever number we're trying to assign to a block. And the second argument is going to be the block that we're applying this mass to. I'm going to call that BLK. Inside this function, we're just going to assign that mass, and we're going to update the size too. We're going to use the same method that we used in the constructor function of the block class. So that's going to be converting the mass number to a string, checking the length of it, and then multiplying that by 10. And then after this update takes place, we're going to render the scene. To make this function work now, we need to add an event listener to both of the mass inputs. So in the callback function here, I'm going to enter an arrow function that's going to take the event as an argument. And whenever you use add event listener, when the function you define gets called, it's going to be passed an event which has certain properties on it. So we're going to call that E. And then I'm going to call our update mass function. The first argument that this function needs to take is the mass, and so that's going to be e.target.value, and that's going to be whatever value is in that input. And our second argument is going to be block 1 because this event listener is being put on the M1 input. And down here, this is meant to be M1 input like that. So I'm just going to duplicate this line and make it for the M2 input. I also just noticed that we forgot the dot length on this guy here. All right, so checking the browser again. Now when we update the mass of block 2, we should see it change size. And that's working nicely. If I refresh this page, these two inputs are empty by default. I'm going to fix that really quick. We're going to store the initial masses of each block into variables. So up with the other block variables, we're going to add a B1 mass and a B2 mass. And then in the init function, we're going to set the two inputs to those values. All right, looking good. So we can run the experiment now and check that it's working. So when mass 1 is 10 and mass 2 is 1,000, this is one of the mass ratios where the number of collisions should start to look like pi. So you can give that a check right now. So 3, 1, we got the first two digits pi. So if we add another 2 zeros to mass 2, so this mass ratio should work too. It's going to give us 3 digits of pi, so we're going to get 314. But when we run it this time, you're going to notice something a little bit funny. All right, so we got the right number. We got 314. But when mass 2 started pushing into mass 1, it started to leave the frame on the left side of the screen. And there's actually a really simple reason for this. So back in the code here, you can see that in our loop, we're only running our physics at 60 frames per second. And 60 frames per second is going to work fine for rendering the scene. It's going to look smooth like that. But we're not running the calculations frequently enough that are going to be updating the positions, velocities of the masses, checking for the collisions. All that's running way too slow for this to work properly. Before we start fixing this problem, I'm going to pull all the physics-related lines out of this looping function and put it in their own function called update. So we got our looping function looking a little cleaner now. So now the question is, how do we get our update function to call multiple times per loop and also to receive an accurate delta time every time it runs? So the first part of the solution is to put update inside of a while loop. And we're also going to manually define our own DT here. So this DT is usually around 16 milliseconds, which will be 60 times a second. That's too slow. We're going to manually define our own DT. And the value we're going to put in here is going to be 0.0001. And this is in milliseconds. So 10 million of these is going to go by every second. So this still isn't ready to go for a few reasons. One, we just have this while true here, and that's never going to exit. We're also defining DT in two spots. And while we're not using this DT right now, This value is still going to be useful. We're going to call this frame time, and that's going to be the time that passes between frames. Now we still got to break out of this while loop, and this is going to run as fast as it possibly can, but it only needs to do one frame time worth of work before it exits and triggers another frame. So now we're going to make a new variable called accumulator. And this variable is going to hold all of the time that hasn't had physics performed on it. It's going to start at 0, and right after this first frame goes by, we're going to add that frame time into the accumulator. Then every time this update function runs, we're going to subtract 1 dt from the accumulator. And lastly, we're only going to enter this while loop if the accumulator value is greater or equal to dt. So let's check to see if this is working. I'm going to add 5 zeros onto here and let this run. All right, that one worked that time, and the block didn't get pushed off the screen at all. I'm going to get rid of this console log in here so it's not logging a million collides. And I'm going to run this one more time with a block ratio of 1,000,000,000 to 1. All right, so we got 1 mass unit versus 1,000,000,000. There we go. We got 3141592. So we're starting to show pi up there. We had 1,000,000,000 to 1. This block didn't get pushed off the screen, so looks like that's working. So that's going to be it for today's project. I know I didn't get around to showing how to put these masses above there or formatting it with the commas, but that's not too hard to figure out. If you guys want to see how that's done, I'm going to leave a link to the GitHub repository of my final code. So feel free to check that out there. So leave a like if you like this video, and thanks for watching.